Chapter 5, titled Design for Different Types of Loadings or Loading, has two sections. One deals with, and it's somewhere in the middle, with design for static loading, different failure theories. We learn a little bit about this when studying Moore circle. We learn about equivalent stresses, von Mises stress and Tresca stress. And then the rest of the chapter, it's about fatigue loading. So let's look at the section on static loading equivalent stresses. If we have a state of loading, complex state of loading with non-zero sigma 1 and sigma 2 principal stresses, or it could be sigma 1 and sigma 3. You'll see there are diagrams where sigma 2 occurs was replaced with sigma 3. So question is, how is the material going to respond when failure does occur? We looked so far at the simpler cases where the stress, the axial loading stress is compared with the yield strength of the material. But again, we can have combinations of stresses and would like to know their effect. And the two failure theories that are discussed with ductile materials, the maximum shear stress theory, and then the other one is distortion energy or maximum distortion energy theory, where the equivalent stress is von Mises stress. The equivalent stress for maximum shear stress theory is the Tresca stress. So again, for a state of loading, sigma 1 and sigma 2 non-zero, we can have what is called a load point in the in this two-dimensional plane. And for a given material with given yield strength in shear, which is approximated many instances as half of the yield strength in tension. Yield strength in tension is the easiest to measure experimentally. Failure occurs if we are outside a boundary, and for maximum shear stress theory, the boundary is this hexagon. Limits of the hexagon, this is on normalized axis, you can see here 1. These are the yield strength in tension, and then likewise negative values. Ductile material, meaning that they have same strength in both tension and compression. That's why the symmetry of the figure. Okay, so including a design factor, the stress is considered safe if we have this inequality holding. So maximum shear stress, it's less than the yield strength in shear, less equal, divided by design factor, or with this approximation, yield strength in shear divided by 2 divided by the design factor. The maximum shear stress is diameter of the Moore circle. Remember, so sigma 1 minus sigma 3 divided by 2. The principal stresses, the largest positive and the smallest of them, or possible negative. And this is again Tresca stress we learned in previous chapter about. The other failure theory, distortion energy theory, there we looked at an equivalent stress calculated with this equation called von Mises stress, and if the equivalent stress is less equal to yield strength divided by design factor, the design is considered safe. So the safe zone is this ellipse corresponding to this equation 5.9, And if you're inside of the ellipse, you're safe. If it's outside, you're not safe. Or failure can occur for n equals 1, that is. The two theories coincide in results for the simpler case, unidirectional load cases, with distortion theory being more inclusive, that is the other one, the maximum shear stress theory being more conservative. Experimental points generated for ductile materials tend to accumulate or show around this in this arched portions rather than in straight line. This is, by the way, called shear diagonal, and the intersection with the boundary corresponds to this case. That is sigma max is half of the yield strength in shear. For maximum distortion energy theory, it corresponds to that is tau max equals yield strength divided by square root of 3. And this is the case, consider here the pure shear loading on the shear diagonal, and the intersection with the boundary again, it's yield strength over square root of 3. Both are considered as approximation to the yield strength. So one was yield strength in shear when you know yield strength is either half or less conservative. You take it as 1 over square root of 3 times the yield strength. For brittle material, where the tensile properties and the compressive properties differ, the failure theories, there are 3 that are presented here. One is the maximum normal stress theory, and being brittle material, we're going to include necessarily the stress concentration factor, because that has the effect of locally increasing the stress in the material, and if a crack starts at the area of localized overstress, then that can propagate and failure, fracture can occur. So a safe design would be one where this inequality holds, and including a design factor, and with sigma 1 being positive and sigma 3 being negative. It's the way they show. So again, sigma 1 goes with the ultimate tensile tension, sigma 3 goes with the ultimate strength in compression, and for brittle materials, usually this is a bigger value. The boundary of the maximum normal stress theory in the sigma 1, sigma 3 coordinates is going to be this square, and failure occurs when you have combination sigma 1 and sigma 3 that project into this area. So this is area of failure for real brittle materials. That's why these alternative theories, so Coulomb-Moore theory, that's where the boundary is reduced to by connecting with lines these 2 points, a pair of points, and these 2 pair of points. This is too conservative, so there will be areas that the material still holds and are not captured by the Coulomb-Moore theory. So this would be the equation of this in the set of boundary. And in terms of inequalities and using the design factor, also we're given these two equations. The most widely used, and this is the one that I'm emphasizing, is the modify Moore theory. So the boundary of the safe zone corresponds to an extended point, like you see here, a negative ultimate strength in tension, negative ultimate strength in tension, and you close it with these lines, and they are closer to experimental data. The way we use this kind of graph is by placing what is called a load point. So you calculate using Moore circles, sigma 1 and sigma 2, or sigma 1 and sigma 3. You position on the sigma 1, sigma 3 graph, and that's the load point, connected with the no load point, and that's the load line. Where the load line intersects the boundary, that's the failure point. Design factor, it's calculated as, if not already included with the load point, it's calculated as the ratio between the segment from 0 to failure point divided by distance from from origin to the load point. Okay. All right. So this was about failure theories. Again, for brittle material, modify Moore. For ductile material, distortion energy theory. You need to be careful when applying them. Distortion energy theory works with ductile, like steel and aluminum and titanium. It doesn't work with plastic, doesn't work with wood, so be careful. This is the first choice in reporting stresses on final MM packages. You need to understand what the meaning is. All right, so let's move to now to fatigue failures. Everybody knows that you can break a piece of wire, thin wire like aluminum or copper wire, by banging it back and forth, and that's called fatigue. Actually, it's called low cycle fatigue. We recognize the minimum maximum stresses on a location, on a point on the surface of on the part, and we can calculate mean stress. We can calculate amplitude of the stress. So mean stress, sum of the minimum maximum, amplitude difference divided by 2, and then we define stress ratio R. This is the one that we'll be using it in this book. So minimum stress over maximum stress. Static loading means that it's one time loaded, and that's it's left as is, being the case of structures, of buildings, where the fluctuation in loading is minimum. Think occupants to a building, their mass is very small compared to the weight of the building itself. Graphic wise, the stress, the fluctuating stress can have this appearance where they vary the same amount about a zero mean. I'm telling you now, this is the most has the most damaging effect upon the material. When you want to break a wire, what you're doing, you bend it back and forth in the same amount in both directions. And then we can have, in terms of stresses, they could be, and that corresponds to R -1. R between 0 and 1 would correspond to a positive mean. The minimum value never becomes negative. We can have some negative stress, mean again being positive. We can have a negative mean and some positive stresses, most of them being negative, and then a negative mean, and everything happens in the compressive mean stress. Again, the most damaging, and this one is pulsing stress, with the minimum value being 0, and stress ratio is 0. Okay. All right. So the problem of fatigue failure was first occurred with in the 1800s with rail transportation. And what happened after some time on the use, train car axles, they were failing in an unusual way to what was known then, compared to what was known then. So somewhere in the middle area, you could see from where a fracture started and it propagated, and these are called beach mark, and at a jolt or sudden overloading, there was the final fracture occurring, and this has the appearance of fresh appearance. The image here shows a fracture in a rail track, and the crack started from below. When loaded, it bent, compressive on top, tension below. You can see this is old fracture when it was corroded, and this is the fresh, the ultimate fracture when the material was no longer able to hold. So this is an example of fatigue failure when the type of loading was pulsing. Was pulsing like here. So we had no load when there's no train on the track, and maximum load, and we have maximum load in tension below where the crack started, the lower area of the track. Anyway, so what Moore did, I need to go the other way. What Moore did was to replicate in the lab what he saw happening to the rail axles. So he prepares specimens, many of them, and or at least nowadays this test is standardized, and the specimen is prepared where it looks like hourglass, the minimum diameter here 0.3 inches or 7.62 millimeter diameter, mirror polish. So mirror polish, and it's supported at two ends, and then there is a yoke and there is a load, and this load can be set to certain value, to chosen values, and then the specimen is rotating, and the number of rotations are counted until failure. If failure occurs, so because below certain load, you can rotate this specimen indefinitely without any failure. Due to the way of supporting and the way the load is applied, the area, the test section experiences no shear, only pure bending. Same as with the actually with the rail wheels, because the supports, rather the bearings, this is only one side, but can you imagine one bearing is here and the other bearing is the opposite way. Wheel taking the reaction from the track would correspond to where the yoke is. So many specimens, you put them, you load them at certain load level, run until a fracture occurs, you count how many rotations, how many cycles, and these points placed on a graph, I have here actually from other source, so placed on a graph where the horizontal axis is number of cycles to failure, and the vertical axis is the calculated stress, the nominal stress in the test area. So they tend to accumulate in some fashion. So, and what was noticed was that below certain stress level, the specimen will never break, and that's that maximum stress where failure does not occur is called the endurance limit of the material. Now you must understand, this is a regression line, so there are data point above and below. So likewise for the straight portion of the graph, there are points above and below. So the endurance, what is called endurance limit, would correspond like to an average stress, at which there's 50% chance that the specimen will never break. Okay. So we went through this section. Moreover, we discussed it. Let's see how endurance limit for practical application can be determined. So the graphs, like you saw before, plotted for various materials, they have this appearance. There's on a log axis, logarithm of number of cycles, logarithm of stress amplitude, and again these are reversed bending. R equals -1, like in the test, and specimen mirror polished 0.3 inch diameter. So we have this regression line that's sloped and then moves horizontal, and this is one material: medium carbon steel, low carbon steel. For aluminum, the past 1 million cycles, the curve reduces slope but doesn't stay horizontal. So aluminum doesn't have actually an infinite fatigue life, something that engineers know, aerospace engineers know. Aircraft structures, they have certain maximum numbers of hours of life assumed to them. Anyway, so the slope portion of the shaft has this equation. So amplitude of stress is endurance limit times number of cycle of power b, and b is called exponent, it's an exponent related to the slope of the curve, and Sn is fatigue limit or endurance limit of the material, and that's very well approximated. Sn is very well approximated, was half of the for mirror polished specimen was half of the ultimate strength in tension of the materials. Now, for a part that has other diameter than also reverse bending, that is R-1, but size is different, surface finish is different. You want the probability of failure to be less than 50%, that is, reliability to be less than 50, or rather higher than 50%, let's say 90% reliability corresponding to 10% probability of failure. There are some corrections that need to be done to the endurance limit, and it's called true or actual endurance limit. And you can see here some coefficients that are all less than 1 or at most 1, serving to do those corrections. So one of the so Sn, that corresponds to like I said, half of the ultimate strength endurance limit for a material to assume to be half of the ultimate strength. And then we have Cm, this coefficient is the type of rather it's included with Sn, and so we had the polished, the mirror finished, for which the relationship between ultimate strength and endurance limit is 2 to 1. So for a 120 tensile strength endurance limits is half, 60. For 100 is 50. For other type of finishes other than mirror polish, which is expensive and you cannot afford to mirror polish all parts that are subject to fatigue loading, you can see there is a drop, and it's more the higher strength materials, they are more sensitive to the surface finish versus lower strength metals. Okay, so this is Sn in this equation, corrected with Cm. Cm is a coefficient for what is the material factor? And for work steel, it's 1, but cast steel, powder steel, and other materials that may have inherent defects, like for example, iron has graphite flakes, can act as minute stress concentrators. Cast steel may have inclusions, impurities. Powder metal, which it's form of powder with voids between that can act. The voids can act as trace risers. So we make this correction, multiply with the right coefficient, and then type of stress. If it's bending, like in the Moore test, coefficient is 1. Otherwise, if we have tensile strength, tensile loading, you can see it's less than 1. Why is that? Because in tension, any points in the material over the cross section experience the same amount of stress, and even internal imperfections can initiate the crack, versus bending, where it's the outer skin that it's stressed most, and as you move to the center of the part that is reverse bent, there will be the stress is less. So a defect right in the middle of the part, theoretically, may not initiate a fatigue crack. We said that in Moore's test they were half above, half below the regression line, and that corresponds reliability 50%. If you want to increase that, you need to multiply it with a coefficient that of course will be less than 1, and those are listed those are listed here. So if I want to be 90, just 1% probability of failure, the multiplier is 0.81, as you can see. And finally, we have the size factor. The standardized Moore test specimen is 0.3 inch diameter. Actually, larger parts have higher chances of developing or fatigue crack to develop because the and again we're talking rotational bending. Think of this experiment. You're walking 1 mile, there's some chance to find a penny. If you walk 5 miles, there's 5 times the chance to find a penny, because you travel more distance, assuming that you're looking down looking for pennies. So same with the size. If a larger size specimen has a larger circumference and increased chances of one of the surface defects or right below surface to grow into a crack. Okay, so for correction for size, you either use this chart, and as you can see, if it's 0.3 of an inch is 1, so 0.3 of an inch, and if it grows to 2 inches, the coefficient is approaching 0.8, and would be like 10 inch, maybe a ship shaft. See how much that coefficient CS reduced when smaller by 30%. Alternative to using this chart is to use this table here. So anything that's less than 0.3 inches is 1. Between 3 and 0.3 and 2 inches, use this equation. Over 2 inches up to 10 inches, use this other equation. And the equivalent in SI units. Now, if we're having a rotational bending, like in Moore's test, the equations of or the size, it's calculated based on the diameter. But otherwise, we need to calculate the equivalent diameter. So, if say I have a beam that is flexed up and down, think of a diving board, and there will be a portion of the beam or diving board above, a portion below that are stressed 95% and up to 100% of the maximum stress. So this will be a smaller portion than when you have like a donut, a ring around the shaft. So there are some equations that allows us to calculate the equivalent diameter, to use it with the size factor here. So and they are all listed here in the text. So for example, for a round that is bent, the equivalent diameter is 0.37 of the nominal maximum diameter. And then if it's rectangular, equivalent diameter is 0.808 square root of width times h. Okay, and it explains how these have been derived. So what can influence the fatigue strength of in an application? We already agreed upon some. So internal flaws coming from the way the part was produced, cast or powder metallurgy. And then temperatures, you can see, influences the endurance limits. So higher elevations increase the endurance limit. And then if the material is non-homogeneous, if it has work, recrystallization following welding and tool marks and from turning or from milling, they can act as stress concentrators. If you have compressive residual stresses obtained by shot blasting or peening, those are favorable. So any compressive residual stress are beneficial. If they are tensile residual stresses, those worsen the endurance strength of the material of a part. Corrosion, and the corrosion can exacerbate by starting small crevices of oxidation at the surface from where the crack can grow. Okay, so here's some graphs. Something I said a couple of times, and that's also was highlighted here or underscored. So for the reversed bending, the strength is the least, and for this will be the pulsing loading the material, the endurance limit of the material, it's higher. There are some sample problems. We'll do some on our own. The next section is to where we have a mean and alternating stress type of loading. So Moore's test corresponds to reverse bending, that is R equals -1. What happens if it's reverse bending, then simple comparison with the results of Moore's test, or with the true endurance limit calculated, as we saw, with all those factors, correction factors, is enough. But if we have instead a situation like this one, when there is a mean stress on top of which we have this alternating stress, example being a static load on top of which we have a fluctuation, say in a suspension component. You have the weight of the car, and as it moves on a road due to bumps, and there is fluctuation around that static loading. Or maybe you on a diving board, you move to the end of the diving board, stay there, the board is sagged, and then you squat and do things, and the board oscillates about a mean stress. So how we are going to expand the results of this test with all the corrections corresponding to this type of loading to the cases where we have non-zero mean stress and of course a non-zero alternating stress. And this is what this section is about. So first we need to do a stress analysis and find the mean stress, calculate the minimum maximum stress, find the mean stress, find the alternating stresses, and then based on various theories, we can have what are soon to be different safe zones. So again, same as before, where we had the modified Moore theory for brittle material, here too we have a load point. So you calculate the mean stress, calculate the amplitude of the fluctuation, you position the point in the sigma and sigma A plane. That will be the load point. And then you evaluate that load point with respect to some boundaries. And the most conservative case is where we have for static loading, the mean stress not exceeding yielding, and for the other case, when the mean is zero, the true endurance limit is the other boundary. For static loading, the safe zone would have been the yield line. So if I'm not yielding the material in any way, then the load point is in the safe area. Other boundaries that delimit the safe zone from the failure zone are the Goodman line, and this is the one that we'll be using. Goodman line connects the true endurance limit with the ultimate strength, and of course we don't want to yield the material, so safe zone would be up to the intersection of the Goodman line with the yield line and along the yield line. So okay, let me do this. I go to paint, paste, and I can delimit the safe. This will be the safe zone that we'll be working with in this class. Okay, so Goodman line and yield line combined. Other failure theories are Gerber's parabola. As you can see, it goes experimental points, and this appears to be the closest to envelope data points. A bit more difficult to work with because of its higher degree nature. And then we have the Soderbergh line. I said is the one that connects the most conservative, connects the true endurance limit with the yield strength. Not shown in the book, but referred elsewhere in the referred elsewhere in chapter 12. Let me pause to find that chapter 12. All right, so chapter 12 on shaft design makes use of code for calculating for fatigue shaft that transmits power, that is torque, and they are also subject to bending. And here the failure zone is an ellipse, and this is called ASME ellipse. It's not discussed here, however it's in chapter 5, however it's used in chapter 12. The theory that we're failure theory for mean alternating stress that we'll be using is going to be the Goodman line and yield line combined, like you saw it in the drawn here in red. Note the typo, so this should be SU instead of SY. Okay, and makes sense because it passes through the SU and 0 point, not SY. Okay, and also notice the introduction or the use of the safety factor with the alternating stress, but not the mean stress. And if we're to calculate the design factor, then and again, Goodman line being our preferred theory for mean alternating stress calculations, this is the equation to use, which you can see it's correct. SU here versus what's on the figure. And find mean stress, find alternating stress, calculate the stress concentrating factor, if any, and then you can calculate the design factor N. Design factor is nothing but same as we did it for modifying Moore theory for brittle material. So it's an extension of the load line going from no load to the load point, and you extend it until it intersects the safe zone or the boundary of the safe zone, and you measure either projection or directly on the load line the ratio between the intersection from 0 to the intersection with the load line or rather failure point divided by distance from origin to the failure point, to the load point. So let me go to the back to this and explain. So I'm drawing one. Sorry for this. I'm drawing with blue color, dark blue. Firstly would be a load point. So you calculate the mean stress, you calculate the alternating stress for your problem. The load line, you get it if you connect the load point with the origin, no load. Okay, and then in red is the safe boundary, and we have the failure point. So, and again, this is the load point. So design factor is going to be the ratio between this distance, this distance over this distance. Okay. Or you can work with projection if it's more convenient. So you work with the either horizontal or vertical projections. So likewise would be this distance divided by this distance. It gets you the design factor. But we have the equations, and we're going to use it for convenience. Now remember, you can have two intersections. So you can have intersection with the yield line, and you can have it can intersect the yield line first and the Goodman line second, or vice versa. So you need to calculate the design factor for both cases, intersection with the Goodman line, intersection with the yield line, and of course report the smallest of the two. Okay, and this is the equation for intersecting with the yield line, and of course yielding the stress concentration factor, as you can see here, was applied to both the alternating and the mean stress. Okay. Other means of presenting this kind of problem, other way of presenting mean alternating stress limits are using the Smith diagrams. We're not going to use them. For brittle materials, the stress concentration is recommended to be applied to both the mean and the alternating stresses versus just the alternating stresses like you saw for ductile materials. Okay. In terms of designing for increased fatigue strength, there are a number of recommendations. So we learn about the surface finish, but that's expensive to do all mirror finish. The compressive residual stresses. Remember the stress concentration factors, if you can limit them by having wide fillet radius and minimum number of steps on a shaft blended with wide radii, then decarburizing through heat treatment and grinding, those should be avoided. Remember, the harder grades, the steels they're more sensitive to notches, to surface finishes. For the choice of the design factor, there's some recommendations here. So for ductile material with static loading, this is in general, so static loading up to 2, as you can see here. In general, for machine elements, this is the value that we'll be using, between 2 and 2.5. Higher for unknown dynamic loading and uncertainty in the material's properties. For brittle material, of course, there is no yield strength, so the reference property is going to be the ultimate strength. So for static loading, design factor 3-4. For variable loading, dynamic loading, up to 8. Okay. And some more on design considerations. You may want to read these on your own. Again, knowledge of the condition in which the component operates, like temperature, corrosive environment, all that's things to consider. Again, that it makes for a good reading than me. I could emphasize in a short time. And some sample problems, we'll do our own share of problems from the back of the book. I'll refer you to the sample problems to understand the material better. One last example of so all sample problems. One last example on the or actually a couple of sections discussed are on statistical approach to design in general. So you can have fluctuation in the material property, rather material property and fluctuation in the loads. And shown here is bell curves, assuming normal distribution for both. There is the area of the overlapped curves is the probability of failure, where you high loads meet a weak material. Good quality control will increase the sharpness of the material property distribution. As for loading, of course, limiting the overloads. There are ways of doing this. Any dampeners, if any, or other type of load monitoring is going to limit the probability of failure. But again, we can work on the material, and we can train the people that use the product, say it's a vehicle or an airplane, and reduce the probability of failure. And finally, this the damage accumulation method, first observed with rolling element bearings, and you can have components of a machine operating at different load levels for different amount of times, and the assumption is that these damages accumulate in the or affect the material. According to this equation. So you have so what are these terms? And could be number of cycles, or could be time of operation. So at the given stress level I, the material of the part would fail after this many cycles. You're using it to fewer cycles, lowercase ni. And so what you need to really calculate is the number of cycles to failure for the given load level. And of course, knowing what level of loading the component can experience. So, for example, you have a transmission component, and you monitor, say, for 50 miles or 100 miles, how that component gets loaded. You know, what throttle level, what speed. You can calculate the torque through that transmission component, and they'll give you the number of cycles, lowercase n, for the various stress levels. And then at that stress level, you can calculate how many cycles to failure. This assumes that we are under the sloped portion of the graph. So you don't design for infinite fatigue life. Sometimes that's not economical. I'm sure you agree, if you take you go to a junkyard and you take apart a vehicle that has been on the road for 250,000 miles, you can find components that are like new and could be used over and over on other vehicles. That's not an economical design to have parts that can last way more than it's needed. So Palmgren Minor rule, this approach to design applies to that kind of instances where you want to design for limited life. And so yeah, it allows you to calculate this DC cumulative damage. And again, was started by Palmgren and Minor observing failure of rolling element bearings. There are some problems. I have some problems that I formulated my own, and we're going to look at them in a different recording. So this being said, I'm going to stop here. Again, the book remains your main reference. I hope I introduced you to the subject. This is a rich chapter, 43 pages. We'll learn the material as we do problem.